So I want to take a look at the sum, this guy right here. I'll just write it out. Sum from n is equal to 1 to infinity of 1 over n squared. Pretty famous. This is known as the Basel problem. And I want to tackle it in a way someone might be able to think of. So yeah, I'm going to just get straight into it. But first, I want to consider something. Well, you can't just tackle this directly, right? Like, I can't think of a good way to just directly deal with this. So let's take a look at another infinite operator that's applied to something that looks like remotely similar to this guy. But I'll explain why it's important to us. Okay, and what that expression is going to be is the infinite product formula for this guy right here. Sine of pi x over pi x. And in many proofs, you'll actually see that they do begin with the Weierstrass factorization for this guy, which is what the infinite product is known as. And I'll go ahead and write it out and explain why it's so cool. So infinite product, we use capital pi to represent that. And we're going from n is equal to 1 to infinity. And inside here, we have 1 minus x squared over n squared. And so, yeah, why is this cool? Well, we have this over n squared. That's the cool part. Now, you may notice that there's a lot of other garbage, right? First of all, there's a negative. There's an x squared that we somehow got to deal with. And we're subtracting this from 1. And most importantly, this is a product. It's not a sum, right? So how are we going to use this? We're going to take advantage of this property. We want to turn this guy right here, it's a product, into a sum, because that's what we're trying to deal with, right? And I'll just write it right here. This is our end goal, to find whatever this is equal to. So this is a sum, this is a product. How do we turn this into that? Well, let's recall that if we want to turn a product into a sum, we can just go ahead and take the log, right? Because logs have this cool property. Log of a times b is equal to log of a plus log of b, right? So basically what we've done is by taking a logarithm, we've turned this multiplication into addition. So in a similar manner, we can actually turn this infinite product into this something that looks kind of like this, right? It has a sum at least. So let's go ahead and do that first. Okay. Let's go ahead and take the log of both sides. So on the left-hand side, now, let's just go ahead and, yeah, you know, I'll write it like this, and then later we can deal with it. Okay, and on the right-hand side, we also want to take the log, and we have our capital pi. Just drop the marker in the most, whatever. All right, capital pi, which stands for product, going from n is equal to 1 all the way up to infinity. And we have this thing. Okay, so now let's try to wrap our heads around how exactly this right here would work. Well, we have log of an infinite expression on the inside, right? So it's going to look something like 1 minus x squared over 1 squared times 1 minus x squared over 2 squared, right? Times 1 minus x squared over 3 squared, so on. Because all you're doing is just, this is a product, right? And you're just changing the value of n each time. Okay, well, as we said earlier, this is a product. And if we have log of a times b, we can turn that into log of a plus log of b. So, similar to what we did back then, we can do this right here, right? Just take log of each of these guys and then add them up. That's basically what it's trying to do. So log of 1 minus x squared over 1 squared plus, right, they're multiplying, log of 1 minus x squared over 2 squared plus, and so on, right? So how would we abbreviate this, right? How do we write it using one of these? Well, simple. Notice that the only number that's changing right here is just this 1, this 2, this 3, so on. So let's write this infinite sum right here, going from n is equal to 1, right, and then off to infinity, like that. And then everything else is the same. So we still, every term is going to have this log of 1 minus x squared over, right? The only thing that's changing is this bottom right here. So 1 squared, 2 squared, 3 squared. We're going to just have n squared. Okay. So what we really just figured out is this guy is equal to this guy. So let's write that in. So on this left-hand side right here, let's go ahead and deal with something first. So this fraction is kind of ugly. We can also go ahead and split this up using a log property. This is just log of the top minus log of the bottom. Right? Because this is division inside. Now over here we saw that this guy here is really just equal to this. And that's pretty cool. Because all we did is, well, the log of the product is the sum of the log. Really, that's pretty cool to think about. N is equal to 1 to infinity of, well, this right here. Log of 1 minus x squared over n squared. Okay, now, we have the log, right? Earlier, only reason why we wanted to do this, why we wanted to take a log, was to turn it into something that looked more like that. But now everything in here, this is what we're trying to work with, is trapped inside of this logarithm. So how do we deal with that? Well, if we maybe take the derivative, right, then the inside springs to life. Because what really happens when you take the derivative of, say, 1 over x? Oh, sorry, no, not 1 over x. Log of x. You just get, well, 1 over x, right? So essentially, you're freeing up whatever's trapped on the inside of the argument. So if we just take the derivative on both sides, then that gives us this guy out again. And also gets rid of all of these other logs that might be kind of hard to deal with. So let's take the derivative. On the left-hand side, let's take the derivative of this term first, right? So the derivative of a log is just 1 over whatever's on the inside. So I'm going to go ahead and write it like that. Okay, but chain rule says we have to take the derivative of the inside function too. Not just the outside, but the inside. Inside is sine of pi x. The derivative of the sine of pi x is, well, the derivative of sine is cosine. So let's just go ahead and write down cosine of pi x. Right? I'm writing it like this fraction, simply because, well, if you just multiply it on, that's the same thing as having it being in the numerator. Okay, and then one last thing. We took a look at this function, and one more time we have to apply chain rule. Look at the very inside function right here. The derivative of pi x is just pi, so we can also go ahead and multiply on a pi. Look at that. Okay, next. This minus sign is going to stay. Now, earlier we took a look at the log of a times b thing, right? We saw we can split it up into log of a, in this case we have pi, and then plus log of b. Now, if we take the derivative of this term right here, then this log of pi is just a number. So this guy is not going to matter to us. So all we're left with is this natural log of x. The derivative of natural log of x is just 1 over x. So this is pretty easy. Right-hand side. The derivative of the sum. Now, this sum converges absolutely and uniformly. So therefore, what we can do is we can just swap the order that we take these two in. And if it doesn't really compute what that really means, why would you swap the order? Doesn't that change it? Well, think about it like this. If we have this derivative, right, and then we have this infinite sum, a plus b plus c plus d, ... right? Well, what we can do is, because they're all adding to each other, we can take the derivative of each of them. So the derivative of a, right, plus the derivative of b, and sorry for my sloppy hand, I'm just trying to jot this down really quickly, the derivative of c, and so on, right? So taking the derivative of a sum is just taking the derivative of each of the terms and then adding them all up at the end. So this is basically just moving the sum to the outside, right? You're taking the sum of the derivative of each of these guys. Now, because they're both limit processes, right, there's a lot more rigor that has to go into it, but that's the basic intuition behind it. Now, it's not always going to work, but it works for us now. So there's a derivative on the outside here, right? We applied a derivative. We can just go ahead and change the order, as I explained earlier. So n is equal to 1 to infinity, and then we're now taking the derivative of this right here. Log of 1 minus x squared over n squared. Okay. So how do we do this? Well, it's just another log, right? And there's a whole reason why we're doing it is to unlock the inside. So right here, and we also saw what the derivative of log was earlier. It's just 1 over whatever's on the inside, right? So you get 1 over whatever's on the inside. X squared over n squared. Okay, well, so we took the derivative of that. Chain rule says there's another function on the inside. So we also have to deal with that. Okay, so what's the derivative of the inside? We have to multiply it on. The derivative of 1 is just 0, so we can just go ahead and ignore that. So all we're dealing with is the minus x squared over n squared right now. So we're trying to find the derivative of minus x squared over n squared. And this is really all that difficult. The minus 1 over n squared, that's just a constant. So we can just pull it outside. And all we have left is just this x squared. And the derivative of x squared is just 2x. So we have 2x times negative 1 over n squared. You can also go ahead and move this 2x up on the top. So 2x over n squared. And don't forget this negative sign. Okay. This right here can be simplified a little more. Notice that this right here is just multiplying into both of these terms, this one and that one, right? So let's go ahead and distribute that in really quickly. We can also move this negative 2x up on top. Okay, so we just distribute this into either term. N squared times 1 is just n squared. We saw this minus sign right here. N squared times this thing, well, n squared over n squared cancels, so all you're left with is this x squared. Okay, cool. So we have this and that. So all I'm going to really focus on are these two sides. Okay. So what was the purpose of doing all this? Well, we wanted to find something that looked kind of similar to this right here. And we've almost got that, right? It's just we have this pesky minus x squared for some reason, but also the numerator isn't 1. So what I want to do is divide both sides, both this side and that side, by negative 2x, right? So that way we're left with the 1, and it looks more like that. Okay, well, to divide everything by negative 2x, first of all, I want to simplify this a little bit further, right? We can keep the pi there. But notice that cosine over sine is actually cotangent. So we have cotangent of pi x. Okay. And we said we were going to divide everything by negative 2x. So all this does is give us negative over 2x, right? Dividing by 2x. And same idea over here. Negative 1 over x, we're just dividing it by negative 2x, right? If we just multiply this in, the negatives cancel, you get a plus. And then the 2, we just move in. X times x is just x squared. So 2x squared. Okay. So, yeah, this is equal to, well, we divided negative 2x on both sides for the sole purpose of getting rid of it from the inside of this sum. So the top, all we're left with is 1 over n squared minus x squared. Okay, so this is what we're working with now. I want to turn this guy right here into an addition. And, well, how do we do that? You have to make a substitution, right? So just bear with me for a second here. Let's let x equal to negative it. Seems like pretty out of the blue, but it ends up working out for us. So make a substitution. Let x equal negative it. Just replace all of the x's with negative it. Right? Okay, so what do we get? Right here, first term, negative pi times the cotangent of pi times x, but x is negative it. Okay, and then 2 times negative it. So here you notice that this negative right here cancels out with this negative. So we'll deal with that in a second. Plus 1 over 2x squared, but x is just negative it. Okay, yeah, let's go ahead and deal with this later. In here, we want to turn it into a plus, so now we've got that, right? Summation going from n is equal to 1 to infinity of 1 over n squared minus negative it squared. Okay, let's dive a little more deeper. This first term is pretty easy to comprehend, right? We still have this pi cotangent and negative pi it, right? Whatever. Negative pi it. And bottom we just have this 2it. Okay, what about the second term? Well, this 1 and this 2 are still going to be here. How do we square this guy? Just square each thing that's being multiplied on, right? So we're squaring this negative. That's just going to give us a positive, right? So we can just go ahead and ignore that. Squaring the I gives us a negative 1, right? So essentially we're just multiplying on a negative 1 on the inside. And then finally squaring the t just gives you t squared. So you just get 1 over 2t squared. But keep in mind that this actually changed into a negative. Okay, and finally, on the right-hand side right here, 1 over n squared. And the same idea is right here, right? This is exactly the same expression. The negative, it's square it, you can ignore it. I squared is negative 1, right? So, negative 1. And then t squared is just t squared. So, and we can go ahead and rewrite this double negative as a positive. So, what do we have? N squared plus t squared in the bottom. Okay. So we're getting closer. We're inching ever so slightly closer to what we want, which is written right up there. But how do we go about this now? Well, I think the only reasonable thing to do here is, well, if we didn't have this t, then we already have our answer. So let's just let t approach 0. Let's see what happens, right? Now, on the left-hand side, notice that, first of all, if you let t approach 0 in this term, you get a negative infinity. So that's already not nice. This dividing by t also approaches infinity, but then you also have a negative cotangent of something. Well, if you just go ahead and plug in a 0 there, cotangent of 0, pretty sure that's actually undefined. So we have something weird over something infinity. It's not going to work. So let's go ahead and change this into an alternate form. Let's use Euler's formula for this. Okay, so I just went ahead and really quickly moved everything that we had so far back up to the top. And I was saying Euler's identity, right? How the hell do we apply that here? Where do we have e to the I whatever? Okay, well, I mean, let's just go ahead and take a look at it and see what we can do with it, right? E to the it, or rather I'm going to use e to the I theta, is equal to cosine theta plus I sine theta. And this cotangent is pretty hard to deal with as of right now. And you see that we actually have these trig functions that we can represent in terms of e to the I, whatever, right? We'd rather deal with an exponential than a weird trig function. So let's go ahead and see if we can replace this guy with something involving this. Now, cotangent is just cosine theta over sine theta. So this is what we're going to aim for eventually, right? Just keep this in mind. Okay, but this doesn't come so easy, right? Let's go ahead and find cosine first in terms of this. Well, how do we do that? Let's input negative theta instead of theta. So wherever there is a theta as of right now, let's go ahead and replace that with the negative theta. So why do we do that? Well, this actually gives us a really nice way of working with this, because this right here simplifies down nicely, right? You just get e to the negative I theta. However, on the outside, right side, cosine is even, meaning the negative, it doesn't really matter whether the inside's negative or not, right? It's going to output the same value. So the negative can be there, or it can't, or it doesn't need to be there. So you can just go ahead and replace this with cosine theta. Now, sine, on the other hand, is odd, meaning if you have a negative in here, then you can also just move it to the outside, right? So let's go ahead and do that. Minus I sine theta. Okay, so let's get rid of all the scratch work in between. These are two equations that are always true, right? For any value of theta. Pretty cool, right? Because now this is really, we can use these as two equations. If we add them, notice that the I sines, they cancel out. So what we get is just the cosine part left. So adding the two, right? On the left-hand side, we just have this plus that. Okay, on the right-hand side, this plus I sine and this minus I sine, they cancel out. So all we're left with is cosine plus cosine, which is 2 cosine. Okay, cool. So all we're left to do is divide both sides by 2, and we're done. E to the I theta plus e to the negative I theta all over 2 is cosine. Okay, so that's part 1, right? We have our cosine. Now what about the sine? Well, for the sine, I'm going to go ahead and move this over. So we saw that adding it made these opposite signs cancel, right? So what if we subtracted it? If we do this minus that, well, left-hand side, once again, you can't do much with e to the I theta minus e to the negative I theta. On the right side, cosine minus cosine gives you 0. So this term now cancels out, and all we're left with is this right here. I sine minus negative I sine, that's just I sine plus I sine, right? Double negative makes it positive. I sine plus I sine is just 2 I sine. And we're looking for a sine theta, right? That's the second part to this. So let's just go ahead and divide both sides by 2i. Alright, so we have this. So we have this, and we have that. Let's go ahead and plug it in and see what cancels out, what doesn't. Okay. So this up here, cosine is that thing, e to the I theta plus e to the negative I theta all over 2, divided it by, and I'm going to get rid of this now, right? Sine, which is this thing. So e to the I theta minus e to the negative I theta over 2i. Yeah? Okay, I'm going to get rid of this now, because all we're really dealing with is that, right? Okay, what can we do? Well, on the top and the bottom, let's multiply. We want to get rid of this complex fraction, right? So we can go ahead and just multiply by 2i on both the top and the bottom to get rid of it. It's times 2i times 2i. 2i over 2i gives you 1, so it's really just multiplying by 1. This 2 and this 2 cancel. And then this 2i and this 2i cancel. So what are you left with? On the top, you have an I. And then you have these guys. They're still up here. Okay. And on the bottom, well, everything cancels out. You're just left with whatever's on top. Okay. So we are done, but everything still looks just a tad bit messy, right? We have this negative exponent up here. So let's just get rid of that by multiplying both the top and the bottom by e to the I theta. Once again, something over itself gives you 1, so this is just multiplying by 1, doesn't change it. So on the top, I is just a constant, right? So we can really be just multiplying it out here. We just need to focus on these terms. Okay, on top, e to the I theta times e to the I theta, it's just the whole thing squared, or in other words, e to the 2 I theta. Okay. Next term, e to the I theta times e to the negative I theta, well, they cancel out, right? Positive exponent, negative exponent, they cancel out and they just make 1. So, like this. And you can see that's already looking much cleaner. And the bottom, the same story, right? This times that is e to the 2i theta. And this times that cancel out to make 1. Okay. So we have that cosine over sine, which we know is cotangent, is just this guy right here. So let's go ahead and plug this in for that and see where it takes us. Okay. So I'm gonna move this pi over 2it over a little because this is a pretty big expression. Still easier to handle than this weird trig function that we don't encounter that much though. Okay, let's just write this down, right? I times e to the 2I theta, right? But theta is just whatever's on the inside here. So what we really have instead of theta is negative I pi t, right? Plus 1. Sorry, I'm gonna write this in red. Okay, over on the bottom, we just have e to the 2I theta again. Sorry, I'm gonna put this down in red. And theta is just whatever's on the inside, negative I pi t, minus 1 instead. Okay, so we've gone ahead and replaced that. What do we still have left to deal with? This guy right here. Let's just put down the rest of the stuff, honestly. Okay, so we've put that down. Next, let's make some cancellations, right? This looks pretty messy right now, but it will simplify just a little bit before it gets messy again. Okay, so this I over I, right? This I on the bottom here cancels with this I on top. That's cool. I times negative I. Right here, if we have this, then I times I is just negative 1. So I'm going to move this negative outside, and then we're going to have I times I on the inside. Negative 1, just positive 1. So having this I times negative I right here is just the same thing as multiplying 1. So these guys really, in a way, they cancel out, right? I times negative I just gives you 1. So all you're left with is e to pi and t. E to the 2 pi t, right? Okay, so let's see what we have. Pi over 2t, because the i's canceled. And then on this fraction right here, we have e to the 2 pi t plus 1 on top, and then e to the 2 pi t minus 1 on the bottom. Okay, and we still put down everything else once again. So dull. Okay. Now let's see if it's easier to think about as we take the limit. Well, once again, this guy is going to approach negative infinity, right? Since if you let t approach 0, then this number grows bigger and bigger and bigger. Well, actually, no, yeah, just grows towards negative infinity. There's a 0 in the bottom here. And that's basically all I need to say. So this is just positive infinity, negative infinity, infinity minus infinity, still indeterminate. What's really fucking us up here is this guy, right? This guy's sitting out here alone. So let's go ahead and try to combine these fractions and see where that gets us. Okay, well, on the bottom here, let's try to make this 2t squared. So to do that, we just multiply a t on both the top and the bottom. So now we have the 2t squared part in this term right here. But then again, we also have all this other junk. And the point is to make the denominators the same, right? So on right here, we have the 2t squared here, right? Now we just have to multiply in this thing, basically, right? So let's just multiply this guy on both the top and the bottom of this. So on the top, we get e to the 2 pi t minus 1, right? That's this guy times 1. And then we have this 2t squared times e to the 2 pi t minus 1, right? And the right side stays the same, so I'm just going to write this as equal sign instead, because all we're really doing right now is simplifying the left-hand side into something we can think about, and then we'll come back to this sum later after we can, get this to stop looking so horrible. Okay, let's combine the two now, right? So you see here that the denominators are the exact same. So everything is now over that denominator, but let's work on the numerator first, right? So the first one, you have pi t times these guys, e to the 2 pi t plus 1. minus this, right? But this negative, we can just turn into positive by reversing the order of subtraction. So we can have this be plus 1 minus e, right? All it's doing is distributing the negative sign. So here we just have negative e to the 2 pi t plus 1. And on the bottom, we now have this slightly better looking denominator, 2t squared e to the 2 pi t minus 1. Okay, right here, let's go ahead and distribute this out. So here we have pi t e to the 2 pi t plus pi t. And then right here, everything's the same. In the bottom, it's still gonna stay more or less the same, right? Okay. So now let's try to think about this again. What happens as we let t approach 0? Does this work out or not? Well, on the right-hand side, we saw that letting it approach 0 it just gives us what we wanted, right? The 1 over n squared guy. On this, however, it doesn't work out as much. So there's a t here, right? So I'm going to write this all in red. This t zeroes out this whole term, right? And so does this t. Right here, if we plug in a 0, though, right? E to the something something times 0 is just e to the 0 is just 1. So you have a minus 1 plus 1 over, and then plugging in a 0 where this t is, it just zeroes out the whole bottom. So notice that these guys cancel out, and all you're really left with is 0 over 0. So we can use L'Hopital's rule, right? And of course, let's go ahead and take the limit on both sides first. But yeah, notice how if we do that, this guy is 0 over 0. It's indeterminate. We can use L'Hopital's rule. So, well, first let's write out the fact that there is a limit, right? The fact that we're trying to take a limit. So let's write down this limit on the left-hand side, limit as t approaches 0. And we have, well, that thing. And I distributed this out earlier. So 2t e to the 2 pi t plus pi t minus e to the 2 pi t plus 1 all over 2t squared e to the 2 pi t minus 1. Okay, and we also need to take the limit as t approaches 0 on the right-hand side. But all that really gives us is, well, it gets rid of that term, right? 1 over n squared, that's all we have left. So this right here is what we're going to be looking for towards the very end. Okay, take a look at this. This is what we got to find now. Earlier we saw that this is 0 over 0. We can use L'Hopital's rule. And what is that? Well, it's basically just differentiating both the top and the bottom with respect to this variable right here. So since this is a limit approaching 0, I'm going to notate this as lowercase l. Okay, so all we're really doing right now is taking the derivative of both the top and the bottom. I'm not going to write it out. It's going to take way too long. Okay, so this is going to have to take it slow and steady, work through it term by term. Okay, so that's it. But if you go ahead and plug in 0 again, right? This is the limit as t approaches 0. This right here, you get 1. This right here, this t is just 0, right? So 0 times anything is 0, so this becomes 0. This becomes plus 1, and then minus. Plug in a 0 up top here. This exponential guy just becomes 1, right? 2 times 1 is just 2. Okay. Okay. You can also combine like terms, actually. So I'm going to do that in a second. But in the bottom, there's a t here, there's a t here, there's a t here. All we really have is just 0 minus 0 plus 0. So once again, notice that you have 0 over 0. What does that mean? You can use L'Hopital's rule again. And it looks pretty complicated right now, but it's going to start. Well, it's not even going to start getting tamer. It's just we're going to keep using L'Hopital's rule until eventually we might have something that we'll be able to work with. So if everything is simplified down again, we can't do any more simplification. If we plug in 0 for t, however, we notice that the top gives us 0, unfortunately. This first term down here, 0 times anything is just 0. 0, right, there's a t here, times anything is still 0, and then over here, e to the 0 gives you 1, but you still have this minus 1, they cancel, 0 over 0, unfortunately. So, use L'Hopital's rule for the third time. And hopefully, this actually ends up getting us somewhere, because right now it feels like, you're doing work for nothing. But, we'll see. We'll see. Okay, so let's do L'Hopital's rule again. Now let's see what we can factor out with both the top and the bottom. So, on top, you can factor out e to the 2 pi t, right? So, I'm going to write this down again. Pi cubed, the limit, as t equal to 0. On top, we factor out e to the 2 pi t, but there's not much else. On the bottom, though, there is a lot. 4, 12, and 6 are all divisible by 2. And in each of these terms, we actually always also have a pi. Pi cubed, pi squared, pi. We can factor out a pi out of that, right? And then we also have e to the 2 pi t in each of these terms. So, e to the 2 pi t. Now, before we go ahead and do cool cancellations and stuff, I'm going to go ahead and write this in again. So, on the top, we factor out this guy, right? So, this becomes a 1. And then this becomes, we factor out this guy, right? So, it's going to just disappear. We just have 1 plus 2 pi t. In the bottom, it's a little more complicated, but it's fine, right? First of all, for each of these terms, you can just ignore the 2 pi t. I'm not going to keep saying that. So, I'm just going to cross them out so we don't need to look at them. Now it looks a lot better, right? So you factor out a 2 pi from each of them. 2 pi, dividing this guy here by 2 pi, you get 2 pi squared, and then t squared. Next term, dividing this guy right here by 2 pi gives you 6 pi t. So that's pretty simple, 6 pi t. All right, and then finally, this final guy right here, dividing 6 pi by 2 pi, the pi's are going to cancel. You're just going to be left with a 3. Finally, let's go ahead and cancel these, right? So that's gone. And let's move this 2 pi outside. Pi cubed over pi is just pi squared, and then you have this over 2. And you have the limit as t approaches 0, which we can finally evaluate, because notice that in here, this is not an indeterminate form anymore. 2 pi squared, t squared, plus 6 pi t plus 3. Here, we can just go ahead and plug in 0, right? Plugging in 0 into this term right here makes it 0. Same with this term. Same with this term. So all we're left with is a 1/3. So this is pi squared over 2. And then this whole guy right here evaluates to 1/3. Okay, and then finally, 2 times 3 in the bottom gives us 6. So pi squared over 6. So we saw that this right here, using L'Hopital's rule a few times, right, ends up giving us pi squared over 6. So that's pretty cool.